Nonlinear systems are just that. They're systems that are not straight lines or not flat planes. We're only going to be dealing with 2 variable systems here, no 3 variable systems. The drawback to it is that you can't use the matrix feature of your calculator to solve the system. And this is why I went over the substitution and elimination method with linear systems first, because we're going to use those methods to help us solve nonlinear systems. So chapter 5, section 5 is the nonlinear systems. All right, so we're going to start with a just a system that has one of the equations is not linear, not both of them, but just one of them is a curved line instead of a straight line. So x squared minus y is equal to 4, and the other equation in the system is x plus y is equal to -2. So you got what we've got here is we've got a parabola, because this has an x squared in it, and a plane y. I know that that's a parabola just from experience. So it's got something to do with that shape. And then this one has a plane x and a plane y. So I know that that's a straight line of some sort. So the picture could look like that. It could have just a million different ways it could look. But this is the general idea of what's happening, that we could have 2 solutions to that. We could have no solutions to that. We could have one solution to that. It's impossible to have infinitely many solutions to that, though. Okay? So the rules for nonlinear systems are not as really rigid as they are for linear systems, because you've got so many different things going on. So a curved line really mixes it up. But as far as solving it goes, the same tools can be used as far as the substitution or elimination method. This one is a great example of one that is set up and ready for the elimination method, because when you look at the y's, you got a plane y here that's negative, and we got a plane y here that's positive. So they're opposite to one another already. I don't have to do anything to the problem to make that happen. So what I can do is then add the equations together. When I do that, the y's cancel out. Negative y plus positive y, they go away. On the right-hand side, 4 plus -2 is positive 2. But on the left-hand side, I've got x squared plus x. They're not like terms. So you can't just smash them together. All you can do is write it out just like it says, x squared plus x. So it doesn't yield quite the easy answer like the elimination did with the linear systems. So then you look at the problem, you say, okay, now what do I do to solve that? It's got x squared in it and a plane x. So I need to get it equal to 0 to solve it. So I'm going to subtract 2. So that gets me x squared plus x minus 2 is equal to 0. Then I've got 2 options to solve that. It's a quadratic, so I can either factor it or use quadratic formula to solve it. I'm going to use factoring on this one, and we'll use quadratic formula on another one maybe. But I want to use factoring on this one because we've done a lot of that throughout the semester. So I think it's a good way. 1 times -2 is -2. It's got to add to be +1. So that'd be 2 times -1. And because it's got a 1 in front of x squared, that lets me take the shortcut and say x plus 2, x minus 1 are my factors. So what happens here is I find 2 answers for x. I get x plus 2 equals 0 and solve it, get -2. X minus 1 equals 0, solve it, and get x equals 1. So I've got 2 answers for x. Now I need to get the answers that go with y for those 2 x's. Technically, you can plug into either of the 2 original problems. It doesn't matter which of the original problems you plug into. I don't care, okay? I'm going to plug into the easiest one, which is the one that doesn't have x squared in it. So that's what I want to plug into. So I'm going to hit x plus y is equal to -2, and I'm going to plug in the -2. -2 plus y is equal to -2. Well, add 2. That's going to be 0. So the ordered pair that goes with -2 would be -2, 0. That's one of our answers. And then I'm going to take that same equation and I'm going to plug in a 1. 1 plus y is equal to -2. We'll get y by itself. Subtract 1. That's -3. So the ordered pair that goes with the 1 is 1, -3. So we found two solutions to this using elimination to start with, and then we had to do some quadratic stuff that we done in the past to solve that system. Not super easy, but not incredibly hard either. It just takes one piece at a time and trying to look at those ideas. Let's look at example B. So let's take a x squared minus y squared is equal to 7.82. So I'm going to throw a decimal in there just for giggles there. And then x equals 2y minus 5. Okay. So not the great problem. Is it set up for elimination? Or could we even use elimination? Well, when I look at the first equation, I got an x squared and a y squared. I don't have either of those in the second equation. So that means I can't eliminate that. But the second equation says x equals this stuff. So it's saying x is equal to something. So that should show me, hey, I can take that stuff and substitute it for x in that problem. Okay. Does it make the problem super easy? No, but it does make the problem better because it only has one variable in it then. All right, so I'm gonna square 2y minus 5. So that means 2y minus 5 times 2y minus 5. And I'll multiply all that out. So that'd be 4y squared minus 10y minus 10y plus 25. And then I still got the minus y squared from the original, and the 7.82 over there. And now I got to simplify that left-hand side and get everything together that's like terms. So I got y squared and negative y squared. That'd be 3y squared minus 20y plus 25 is equal to 7.82. All right. When I get there, I see that I have a y squared, a plain y, and some numbers. Anytime I have y squared and a plain y both in the problem, I got to get it equal to 0. So I'm going to subtract 7.82 from both sides to get it equal to 0. So that's 3y squared minus 20y plus, and then whatever 25 minus 7.82 is. 17.18. That's nice. I got a decimal in the problem. That tells me, hey, don't even try to factor that. You're going to use quadratic formula on that. So I'm going to use the quadratic formula for this. So, but I'm going to find y instead of x. So y equals negative b, so 20 plus or minus negative 20 squared minus 4 times a times c divided by 2 times a. So I'm going to use calculator to help me. So negative 20 squared minus 4 times a times c. So 193.84 inside of the square root. And I'm fairly certain 193.84 doesn't have a good square root. It doesn't. 13.92 is what it is. So we have 20 plus or minus 13.92 over 6. What I'm going to do is I'm going to get a decimal approximation for each of those and then plug that back in to this problem for y and get x. Okay, so the hard part is getting your first variable answers with nonlinear systems. With linear systems, that was the easy part. And the second one was the harder one to get. So it flip-flops with nonlinear. Okay. So let's do that. So 20 plus 13 point, what was it? 92 over 6. So I'm going to do that math. 20 plus 13.92 divided by 6. 5.65. So y is equal to 5.65. So we're rounding there, and that's okay. And then 20 minus 13.92 divided by 6. And we're going to get the decimal for that. 20 minus 13.92 divided by 6. 1.01. Okay, so those are my y values. Remember, I had that equation, x equals 2y minus 5. All I got to do is plug that in. X equals 2 times 5.65 minus 5. 2, 5.65 minus 5. I'm using my calculator to get 6.3. So the x value is 6.3. So when I get this ordered pair, 6.3, 5.65. There's one of our ordered pairs. I'm going to find the other one. So I'm plugging in 2 times 1.01 minus 5. 2 parentheses 1.01 close parentheses minus 5. Should be a negative number. Negative 2.98. So get ordered pair. Negative 2.98. 1.01. Decimals in there at the beginning means a little tougher because you got decimals in there throughout the problem. But rounding it can help you out there and make get approximations pretty close out of that. Makes it work out real nice for you for that problem. All right. So not bad, not bad. Let's look at another one. Maybe a similar idea. Let's take example C. We got x squared plus y squared equals 40. I'll go ahead and take this is the equation of a circle that has. Remember we talked about this. I think it was in Math 100. We talked about this, that it's a circle that's got a center at the origin and a radius of the square root of 40. That's how big around it is. And then the second equation, let's do 3y is equal to x. And so nice little problem to deal with here. And let's see if we can solve it. So I see this problem. I see I got an x by itself. Anytime I see I got an x by itself, that tells me, hey, do substitution. Don't even try elimination. If I got an x by itself or y by itself already, go ahead and do a substitution. So much easier. So I'm instead of x, I'm gonna put 3y. I'm gonna square it because the problem had x squared in it. What that does is it makes it work out pretty nice here because I've got 9y squared plus y squared equals 40. Well, 9y squared and 1y squared makes 10y squared. And then it doesn't have the plain y. So that means I can use square roots to solve it. I just get y squared by itself and take the square root. That's nice. So I'm going to divide by 10. Y squared is equal to 4. Hey, that's one I know. I know that one. I can take the square root of 4 and get plus or minus 2. So y is either positive 2 or negative 2. But it's those are both of the y values. I have a problem that it says x is equal to 3y. All I got to do is plug those in. 3 times positive 2 would be 6. 3 times negative 2 negative 6. So we get an ordered pair 6, positive 2, negative 6, negative 2. This one, the picture looks something like that. That's what that kind of a little more slanted on the line, but it's something like that. That's what it kind of looks like. It's a circle with a line cutting through it. We visualize that, but not just incredibly super difficult there. Again, substitution was the method that we used for that one. All right, let's look at another one that maybe uses elimination. I like elimination a lot, and it's good to recognize it in the nonlinear systems as well. So there's an equation of a circle centered at the origin with a radius of 2. Let's do this one. Okay, so that's not a circle. That's what we call, that's a hyperbola shape, which is this, that's the shape that one makes. Actually, I think it's this way that it does it, but it doesn't matter. Doesn't really matter if you know what the graphs look like. It's the algebra that we're after here. This one, look at the y's. I got a positive y squared. I got a negative y squared. Hey, I got opposites on those. That triggers elimination. They cancel each other out. X squared plus 2x squared is 3x squared. Hey, they were even like terms there. That helps a lot when that happens. And 8 plus 4 is 12. Hey, I actually ended up with a pretty easy one to solve here. I can divide by 3. And there I got x squared is equal to 4. Hey, man, that's phenomenal. I like it when that happens, because I can take the square root of 4. I'm pretty good at that one. So I get x is equal to positive 2 and negative 2. All I've got to do is find y now. So you can go back to either of the original problems to find y. I'm going to go back to the first one because it's got less stuff in it. It doesn't have the 2, doesn't have a minus sign. It's just got x squared and y squared in it. So I think I can do that one a little easier. So if I plug in a positive 2 into x squared plus y squared equals 4. So 2 squared plus y squared is equal to 4. So that's 4 plus y squared is equal to 4. And then subtract 4. Oh, man. That's y squared is equal to 0. That means y has to be 0. If I plug in negative 2, same thing happens. I still get y equals 0. So that's good. That means my ordered pairs are 2, 0, and negative 2, 0. You get the same y value for both of them. And that's okay. They're different spots. 2 zeros over here on the right, negative 2 zeros over on the left of the origin. So they're 2 different spots. Just because I have the same y value twice doesn't hurt anything. That's okay for that to happen. All right. All right. Nonlinear systems. Look for the easy ways to solve it. If they're opposites, elimination is the easy way. If one of them has a plain variable by itself, substitution is the easy way. Got to look for those shortcuts on that. It's much easier when you find those shortcuts with nonlinear systems. Okay. All right. Last section is linear inequality or linear programming and systems of inequalities. Okay. So systems of inequalities, we can deal with nonlinear systems or linear systems. We're going to talk about nonlinear ones for just a second. Real short set of that. I'm going to put some graph paper on here so when I draw a graph, it actually looks like something that you would be able to tell something about. If I don't have the lines, I tend to go crooked out of that. Oh, man. Oh, I feel it. Okay. Stretch. Okay. Now, So we're going to take a system of equation of inequalities, that is. So 5.6 inequalities. And linear programming. The linear programming is going to be the easier part here, so don't fret. It's going to be okay. All right, so inequalities and linear programming. So when we're dealing with inequalities, remember we did these in Math 100. You had to deal with shading and dotted lines versus solid lines and that sort of stuff. So when we're dealing with it here, we're going to do the same thing, but we just may have some nonlinear graphs to deal with. So let's take, for example, a set of inequalities. Maybe y is greater than negative 1/2 x plus 3, and then y is greater than x squared over 2. So they both have that divided by 2 kind of element to them. Okay. Now, with systems of inequalities, you're dealing with more than one inequality on the same coordinate plane. So what we got to do is graph this. So what I'm going to do is try to graph each of these. I'm going to use red for the first one, and we'll start with that linear one. So if I'm going to graph that, it's got a y-intercept of 3, and then a slope of negative 1/2, so down 1 over 2. I could graph it, and it's a dotted line because it doesn't have an equal to mark on the inequality doesn't have the equal to mark, so that means it's a dotted line. Yep. And then I want to look at shading for that particular inequality. So I test a point. Remember us doing this? We tested, if I test 0, 0, and plug a 0 in for y and a 0 in for x. That's what I'm doing there. Is 0 greater than negative 1/2 times 0 plus 3? So is 0 greater than 3? The answer to that's no. So that means I'm going to shade away from the origin, which would be above that line. So I'm going to shade this side of that line. I'm shading above that line. Greater than should imply above as well. It's always a good thing. All right, and then let's get the parabola graphed. I'm going to graph it with a blue pen. So that's a 1/2 x squared. If you don't know what that looks like, it's okay. Just plug in some x values. If I plug in 0, 0 squared is 0. So it's going to be right there at the origin. If I plug in a 1, 1 squared is 1. 1 divided by 2 is 1/2. So 1, 1/2. If I plug in negative 1, it's the same thing. If I plug in 2 for x, 2 squared is 4. 4 divided by 2 is 2. So that's there. If I plug in negative 2, it's the same thing. If I plug in, I'm going to do an even number, 4. 4 squared is 16. Divided by 2 is 8. So 4, 2, 4, 6, 8 would be about right there. Same thing over here. So we get that picture, and it's a dotted line. It's a parabola, but it's dotted because it doesn't have an equal to mark. Now we need to talk about shading. You're either going to shade on the inside of the parabola or on the outside of the parabola. That's the sides of it. It's inside or outside. So if I plug in a test point, I cannot use 0, 0 because my graph goes through it. So I got to pick something else. I'm going to pick an easy point like, that one right there, 0, 2. 0 for x, 2 for y. So it's 2 greater than 0 divided by 2. Well, is 2 bigger than 0? Yeah, 2 is bigger than 0. So my shading is going to be on the inside of this parabola because that was true. The overlap is the part that turns green. Okay, that's the solution area is what this is. These are solutions. Here, those are the answers in that darkened area there. It just takes graphing them, and a lot of times just plugging in x values. If you don't know what to do, plug in some x values and work it out, and see what's going on there. Go back to that family of graphs that we talked about back in Math 100. We had all of those different graphs. you get the basic idea of the function. You kind of get an idea of what the shape's supposed to be, and that can help you kind of narrow down what it's supposed to look like when you get done with it. Let's do this. Yeah, I think I got room right there. Let's say we had y is less than or equal to 3x plus 5. And then y is greater than or equal to the absolute value of x, and then a plus 1 on the outside. And so an absolute value function in there, and then a linear one. They both have equal to marks, so that means they're both going to be solid lines, so that we don't have to worry about that so much. But we're going to graph them. So I'm going to go to positive 5 and up 3 over 1 or down 3 left 1, whichever way you want to do that. Put a solid line there. And it says it's greater than or equal to, or excuse me, less than or equal to. So if I plug a 0, 0 in, 0 is less than 5. That's true. So I'm going to shade below that line, which less than should imply below. So there's my shading for the line. And then I'm going to get that absolute value graph going. So absolute value of x plus 1. We know the absolute value should be that V shape. We talked about that in 100. So it's going to shift up 1. I don't know what else it's going to do, but I'm going to plug in some x values. So if I plug in positive 1, 1 plus 1 is 2. If I plug in positive 2, 2 plus 1 is 3. If I plug in negative 1, absolute value negative 1 is 1, plus 1 is 2. And it keeps going that way. So it makes that V shape just like I thought it would. And that's just by plugging in x values. And again, it's a solid line because it has the equal to mark. Okay. Now the shading. It's just like the parabola idea. You're either going to shade on the inside part of the V or the outside part of the V. So I can test 0, 0 because it's not on the line. So if my test point is right there, is 0 greater than or equal to 0 plus 1? Well, that is 0 greater than or equal to 1. Well, it's less than that, so that's false. So that means I'm going to shade away from the origin, which would be the inside of the absolute value graph. So my shading will be on the inside there. And we see this overlap happen there again. So taking systems of inequalities and throwing them into nonlinear systems, because the absolute value is not a straight line. It's that V shape. So it's the same idea as a regular inequality, but you're going to have some different shapes involved. But the shading, the whole graph is your answer to that. It's not necessarily you're getting one ordered pair like you are with the equations. You're getting the whole graph. Okay. All right. That is systems of inequalities. Let's look at linear programming, and we'll be done for the night. You only need one example for this because it's super easy. Okay. So one of the easiest things we've done all semester. I would say easiest thing we've done all summer because we've all been here all summer. So let's talk about linear programming. What you're going to get with this is you're going to get the linear programming part already done for you. And what you will end up with is they will have a graph drawn. And on this graph, they will have some sort of polygon drawn that has corners to it. Okay. And don't think you've got to be too perfect with that. Okay. And this polygon is going to have, they're going to have the ordered pair. You need the ordered pairs for the corners. So that corner is 1, 7. And this corner is 1, 0. Or maybe let's do 1, 2. And then this corner is 6, 6. And this corner is 8, 2. So you get the ordered pairs for the corners. That's the important parts of that polygon. So a lot of the problems you're going to see will have those corners already picked and told to you. Okay. If they don't have them written there, all you've got to do is read the graph and find them. Okay. Get the ordered pair for the corners. That's the only ones that matter. This polygon is formed from a bunch of inequalities drawn on the same graph. Okay. And what they ask you to do is take what's called an objective function or objective equation. They'll call it both things. And they will ask you to maximize or minimize that function. Sometimes they'll ask you to do both. Okay. So maximize or minimize, or let's do both on this one. Maximize and minimize. Maximize, we're looking for the biggest answer. Minimize, we're looking for the smallest answer. Very basic idea there, okay? So what you're going to do is in this objective function, you're going to take these ordered pairs and plug them in and find out the answer, okay? So we're going to take 1, 7, and we're going to plug it into 3x minus y. So that's going to be 3 times 1 minus 7. And we'll get that answer. So that'd be -4 for that objective function. And then I take another ordered pair, 1, 2. And I'm going to take 3 times 1 minus 2. And that would be 1. Okay. And then I take another ordered pair. It doesn't matter what order you go in with these ordered pairs because you got to check them all. So I'm just going to plug in 6, 6 next. 3 times 6 minus 6. 18 minus 6 would be 12. And then the last ordered pair is we're plugging in 8, 2. And so we say 3 times 8 minus 2. That'd be 24 minus 2 is 22. When I look at that, the maximum is right there. The maximum value is 22. The maximum location is at 8, 2. The minimum would be at -4. The minimum value is -4. That location is 1, 7. Okay. They're going to give you the graph. They're going to give you the objective function. All you got to do is get the ordered pairs and plug them in maximum or minimum, whichever one they ask for. Sometimes they ask for both. Sometimes they just ask for one of them. So just pay attention to which one you're looking for. And you've got to try every corner. And where it's at on the graph, you know, our maximum was way down here at 8, 2, and our minimum was way up top. So it doesn't matter where it's at on the graph as far as the polygon goes. It's all in what you get with the objective function. And they're going to give you those things, okay? And that's what I'm asking you to do for the linear programming stuff. Nothing more, nothing less on that. It's really straightforward. And if we had a little bit more time as far as you know, in a semester, like if I in my 140 classes, I make them actually find the box and stuff, and they always gripe and moan about it, but that's okay. But I'm thinking this is the best thing for us right now. So problems that you might need to look at here, section 5.4. I don't know if I wrote that on the other one or not, but if I didn't, I got it there. 5.5, 9 through 41, 5.6, which is what we just did, 29 through 74. And so things going on this week.